morning we saw a bit what is a plant architecture, what are the different terms to qualify the growth process and how it goes. And this afternoon we progressively go towards the notion of programming plants. But before we can get to this part, we need to see how we can formalize the plant growth. And for this, there will be two aspects. The first is what is a plant growth process and how this can be expressed in a mathematical way. And the second is how to describe the plant structure itself. So we'll deal with these two aspects. So what is first the plant development? So as we said this morning, the plant is growing through its meristems. So recognize the different images on the pictures. The first is here the meristem that is growing, leaving on the flank different young organs. In this case, they are flowers. And these flowers, they will extend and become this mature plant after some time. So this mechanism in itself is what we can call a dynamical system. And everything that is dealt with morphogenesis in biology can be seen as a form of dynamical system. In the case of plants, the dynamical system are of a specific nature because the plant, they grow organs and the organs are attached with each other and they form a tree-like structure. So we will see how this goes. If you take the dynamical systems in terms of mathematics, usually people have this in mind. The dynamical system is represented by a variable that is called x, and the x takes its value in a set of values that is usually r to the n, and the system is this x. And to describe the evolution in time of x, you say the variation of x in time is equal to a certain function. And this function, what is important, is that it relies on the state of the system at a certain date t. Okay? So the variation of x will be, in a way, a function of the state of the system at this very moment. What you can remark is that in this usual description of dynamical system in mathematics, the n of the Rn is fixed. It doesn't change in time. And there is a reason for this. So let's use an example. So if you take a pendulum, which is the usual example for a dynamical system. So you describe the state of the system, the x, by the angle theta, and by the velocity, angular velocity of the system. So the theta and the variation of theta with time. Okay, and then you write a dynamical equation like this one, where you say, okay, omega is the variation of theta, and then the variation of theta is described by a certain law that comes from the dynamics of the system, the physics of the system. And what you can, then you solve this, and solving this means how to compute all the states of the system at different dates, knowing the evolution of the system. So the evolution is given by this formula. So knowing the evolution, you want to integrate, this is called integrate the system, starting from a point x0 that you give at the starting point, and then you integrate the system. And then you want to draw some diagrams, such as the phase diagram that relates the value of theta to the value of its variation. Okay? And then you have described your system. So the fact that this will oscillate, you can see it in these patterns. I don't want to enter into the deep into the theory, but you will see that this is necessary to map what we have in mind in a sort of natural and usual manner with what occurs with plants. So if we want to describe this system by a differential equation, by a dynamical equation, we would need to write something like this. Here I say that the function that controls the variation of the system depends on a certain parameter, lambda, and this parameter is itself a function of the genes or of the environment of the system. Okay? So the genes will modify the way the increment of state will change according to f. Usually, it is used to find the value of f. We need to have physical laws or empirical laws to describe how the system changes. But usually, the x here doesn't change in state. It has always the same structure. It is in Rn. Okay? For a structure that is growing like this, it would be difficult to represent the state of the C set by a x whose structure is not changing. Because the structure is always adding new element, like leaf. A plant adds new leaf. A population of cells adds new cells. So how would you describe the system by a number of subcomponents if the number of components changes in time itself? So we would need somehow a function that would also describe the way x is changing of structure in time. So this is a deep problem, and people has struggled with it for quite a long time. One way to circumvent the problem is to say, okay, I don't pay attention to all the elements. I say my meristem is a population of cells. So x will be the amount of cells in my population. But I forget about the cells. I say x is the number of cells. Okay? It's a way to simplify so that I don't pay attention to the structure. And people are always, usually doing this type of thing. If you have a crop, you want to model the development of the crop, one first thing that you can do is say, my crop is an amount of leaves, and or amount of carbon. And you don't pay attention to how this is distributed into leaves. Okay? So it's one way of simplifying the problem. But now, assume that you don't want to make this type of simplification. So how would you describe the x? So the problem is as follows. If you want to discretize this function here, okay, because this is a variation, so it will express a change in the evolution of the state. So a change in the evolution of the state consists of discretizing the function, and I say my x at t plus delta t is my x at t plus my function multiplied by this delta t. Okay? So this is the usual way people integrate the differential equation that was written before. But it no longer works. And why is this? Because there is a main assumption here. The fact that here I use a plus sign, which means implicitly that my x is in a space that contains a form of algebraic structure. I know how to combine elements by a plus operator. Okay, if I want to add two tree structures together, how would I do? I don't have a space where I can make a plus between two trees, at least for the moment. Okay? So how would I do this? There is a second problem here. For the same reason, if I want to multiply something that is related to a structure by delta t, what does it mean to multiply a structure by some number? So you need to define this also. So because this is not directly transferable to the plant systems, you need to be to come back a little bit and to change this way of expressing things in this way, where I do not assume that there is an algebraic structure on the space to which x belongs. And this function now is directly a function of x. So instead of saying the new value is the old value plus something, I said the new value is a function of the actual value, without saying that this will be an increment of it. You will see now how this has been solved in the part. So this is the difficult question first. And to my knowledge, it's not yet solved for a large majority of structures, because you need to have this algebraic way of expressing the things, and we don't have it. But we can have it, we can reach it in specific cases. And we are going to use, to see how it works, in the specific case where the structure is like a string of values, a sequence of values. So it's particular structure. It will change in time because the length of the structure and the number of components will be able to change. And you will see that it is possible to say something a bit more specific about these string structures. And the way we say this, it is called L systems. So the L of L systems stands for Lindenmayer. So it was Aristide Lindenmayer. He was a theoretical biologist living in the Netherlands. And he worked very intensely with Przemek Brzezinkiewicz in Canada, who is still alive. And they, just before he died, or at the moment where he died, they both wrote a very nice book called Algorithmic Beauty of Plants, from which actually the work that I'm going to present here is very much inspired. Okay. So what is a L system? So let's imagine that we have an organism. Here, I take the organism that was taken by Lindenmayer in the original paper, dating from 1968. That is Anabena. Anabena is a filamentous organism that is made of cells, and the cells are able to divide a bit everywhere. You see that the cell is dividing here, for instance. And he wanted to study how this organism could evolve in time. So what he did is simplify the system, the description of the system in a way that was reflecting the divisions of the different cells in different conditions. And what they observed is that if you want to describe this, you need to have 4 types of cells. The cells of type A, I don't enter into the details what means A in the biological terms. So the cells of type A that can be small or big, and the cells of type B that can be small or big. And let's say that, briefly, that they correspond to different polarization of the cells. Okay? Indicated by the arrow. To describe this, and the evolution of this cell, so a small cell will become a big cell. A small cell will become a big cell. So it is written in this way. A small cell A will become a big capital A cell. A small cell B will become a big capital B cell. Okay? And then you need to define how the system will work in terms of development, evolution. And then this is the role of these 2 other rules to tell how this works in terms of division. So a capital A, so a cell that is big, will divide and become a capital B plus a small a. And vice versa, capital B becomes a small b, capital A. And now imagine that being given these rules that actually are abstractions of the reality, you want to describe the development of this organism. So you see that here, I start to give you a bit of a hint. These rules are a bit like the evolution equation. Okay? And we will see exactly how it matches. Because if I give this, I say how the system changes. So it's like dx dt. Okay. So if I start with, let's say, a state in which there is only one cell, and this cell is capital A. It's just, I take this by chance, let's say. So I start with this graphic representation, and I will divide these cells according to the rules. So what sort of rule can apply here? Only this one, which says that a capital A cell becomes a capital B small a. And then my system, which is represented by capital A letter, will be decomposed, or will be producing two cells, a big red and a small yellow, which corresponds to a new state that has change of shape, of structure, that is a capital B small a. And you see that already we are no longer in the classical theory of dynamical systems, where everything are in the same state space with same constant dimension. Okay? Because here the dimension is augmenting by one by one. Okay, now if I continue, it will give the big cell will divide and will give two cells, and the small cell will grow, and then in the end I will have three cells, and my state will be represented by this, and so on. You see that the system is going to grow according to this rule from an initial state, which is A. Okay, so similarly to what I said before, this type of stuff, let's call it stuff for the moment, is able to capture the evolution of my system. Now, how can I formalize this? Because this was a bit like with the hands. If I want to formalize this in terms of mathematical terms, I start with a string, which is my state, and then I imagine that I have a function that I will apply to my string. This is the idea to try to compute the evolution of my string at the next step. And this is where it becomes a formalization, because if I apply this rule of evolution to my string, I define that this corresponds to applying my evolution to each of the components of my string. Okay? And this in mathematics is called homomorphism. Okay? I pass from the space where I am in the space of strings, and I go in the space of letters or one-dimensional space. So here, this is an n-dimensional space, and here, each operator applies on one dimension only. Okay? So I managed to pass from one space, which is a bit complex, and to decompose the problem into smaller problems. And the trick here is that, maybe you didn't realize, I don't know, is that here a string is a string because there is an order between the elements. There is A1, A2, AN. When I apply the homomorphism to my string, the idea is that I will keep the order on the resulting components. So I have A1, A2, AN. Applying the homomorphism to this order will apply to each component in the same order. Okay? And this is why it is homomorphism. And this is very easy with strings. Imagine that we have a bit more complex structure. This would be a bit more complicated to define. Okay? Everything relies on the fact that I keep the order between the two spaces. Fortunately, we will come back to plants at some point. Okay, so let's see how it goes for the string. What we have is that I can take as an axiom, as the initial state, this string. I apply to this string. I apply the rules to each of the components here. And the idea behind is that the rule that will apply is the one that can be selected according to the parent label here. And then you see that I can, in a deterministic manner, compute each of the results of the small application of rules to each of the component. And then you can compute the image of this guy into the string space. Okay? So look what has been done. I insist on this because after we will forget about all this, but it's extremely important for the generalization of these ideas to other levels of complexity. I don't know how to compute the evolution of a string. I use a trick that is a homomorphism that makes it possible to compute in the space of string the evolution of a string. Okay? Okay. So the L systems, they are exactly this. They are a string. We call this rewriting mechanism. It could be called a string evolution mechanism. In a formal manner, it is composed of what is called a vocabulary, which is the set of elementary component letters, modules, alphabet letters. The notion of axiom, that is the initial state from which I want to compute my system. And then, very importantly, the set of rules, P, that is described by these following equations. And the L system, in a formal manner, is a set of three elements, that is the vocabulary, the axiom string, and the set of rules. And I know that if I have this, I am able to compute the evolution of the axiom. Now, there is a notion important, that is the notion of derivation. It's not exactly the notion of derivation that we have in mathematics on continuous spaces, because here we are in discrete spaces, so it would be difficult to define an equivalent notion of derivation, because they are discrete, and I cannot tend to have a variable tend towards each other. So there is an alternative definition, which is the notion of taking a word, applying the set of rules to this word in the way that I presented, and getting the result. Okay, this operation is called a derivation. And now, since I was in the space of string, I compute an object which is also in the space of string, then I can reapply the operation. And the same set P, I can apply a new derivation and get another result, and so on. The process may converge or may not converge, may end, because there is no more, there is a fixed point, or the system may be growing indefinitely. And this depends on the property of the initial string and of the rules. Okay, so one way to represent this, I say that, because you will see these different notations afterwards, this string would correspond to omega or W0, this one to W1, and then I go from one string to the other in the space of strings by applying derivation. So in a way, in the space of strings, I describe a trajectory. Okay, W0, W1. So how this maps with the dynamic system theory? Well, here what you see is that if X is a string representing the state of my biological system, I can compute X at t plus delta t by applying the rules on my string at time t for an amount of time delta t. And the amount of time here, you don't have it. it is assumed that to go from this state to this one, there is delta t, by definition, let's say. Delta t could be 1, could be delta t. It will be embedded in the rules here. For instance, I say, within delta t, my cell is able to pass from a small cell and to become a mature cell. Okay? So there is a formal correspondence, this is what you have to remind, between the mathematical theory or the mathematical formulation of what is a dynamical system with what is occurring in an L system when we describe the system by rules of evolution, which are called production rules. This is why it's a P here, because this is a set of production rules. A symbol will produce something. Any question on this? No? Clear? Okay. So there are many types of L systems. Here I don't want to enter into the details because it's a space in itself, a world in itself. But I can just briefly browse the different concepts. If you have, when you have the rules here, the left here, the left term is called the left-hand side member. And the right term is called the right-hand side. So LHS or RHS. Now, if there is a unique term on the left-hand side, the system is called context-free L system. Because to apply the rule, I only need to look at the current symbol. No context. Maybe I should. Imagine that I have a rule here, A, B, C, D, sorry, a string. And I have a rule that say B becomes a E. And maybe a C that says C becomes a L. Okay. I want to apply this. I don't okay, I didn't say for, I just say for B and for C, okay? So imagine at some point I want to rewrite this. I arrive on the B. I don't need to know what is A. That is A before. I don't need to know what that is C before. I just look at the B, and in itself, it tells me that this should become a E independently of what is on both sides. And this is the same for C. Okay, C becomes a L. So if the A becomes A, and the D becomes EF, so I would have E like this. Okay, so this is context-free. Now we will look at context-sensitive. Okay, context-sensitive means on the opposite, that in order to rewrite the B, I need to look at the context. So I will need to have a rule instead of this one. Now my rule becomes a bit more complex. I say a B become a E only, I will put in this way, only what precedes the B is an A. But if there is a B before, a B becomes a F. So depending on the left context, so depending on what is on the left of B, the rule that will be applied won't be the same. Okay, so this is called context-sensitive L system. Questions? Is that clear?
It can apply also
for the right.
At the right.
Yes, yes. I can look at both terms, but I can look even farther backward or forward. As soon as I cannot decide just locally, it's context sensitive. Okay.
And this is a classification general for grammars?
Yes, but the languages that are induced are not of the same type. So you're right. So this vocabulary applies to Chomsky grammars. So Chomsky's grammars are the grammar of natural language, let's say, or formal languages like in computer science. Okay, you say that, I don't know whether I need to enter into this, but anyway, you need to say that a verb phrase is a noun phrase plus a verb. It's exactly the same as the rules that we have here. Okay. The difference is that in natural language, I will have other rules like this one. The difference is that in natural language, I need to apply my rules until I reach terminal. Like, for instance, a noun phrase can be a determinant plus an article, plus a noun. And a noun can be David. Okay? In order to get a full sentence, I need to apply my rules up to the end, up to I reach the final terms. Because otherwise, I don't have a string in my language. I have an intermediate string that is not defined completely, and that doesn't define the language. In the case of L system, the rules are all applied in parallel. This I didn't mention before, but it's a good moment to say it. Meaning that if I have a string like this, I will rewrite each, it's the homomorphism that says that this is parallel. I need to rewrite each of the symbols at the same time. Okay? In the natural language, it's not like this. I can apply, if you have let's say, David is drinking. Okay, so this would be a verb. This would be a noun. Okay, determinant. There is no determinant, so determinant could be nothing. And this would be the verb phrase. Okay, so you see that here, and I could have even more things here. I could have a verb that would be a verb phrase, could be a verb plus something that determines the verb. Could be another stuff here, a verb determinant. Okay. So you see that to get to the end, and this is the string defining my language. To get to the end, I can apply the derivation any amount of time, independently of each other. The point is that I need to get to the leaves, to the terminal words of my language. In the L system, it's not the case. So I start by a string. I apply the derivation once to all the symbols, and the next derivation, the next output of the derivation, is a word that is valid. Which is not the case, for instance, I apply to VP, I apply my derivation. Here I get this, which is not a word of my language. Okay? So these are the difference between. So what is common is that in both cases, you construct a language, which is the set of all the strings that you can build with your grammar. And it was shown, and it's not very difficult to show it because you need to take counter examples, that the set of context-free L system is not in the language of that are able to be generated by context-free grammars. You need to. It's a bit more powerful. So the languages generated by context-free L system, some of them are in the context-sensitive languages of the Chomsky grammar, but not in the context-free of the Chomsky grammars. So it's a bit. It's just to answer your question. It's due to the fact that the rules are applied in parallel in one case and not in parallel in the other case. Although the definition of this context-free, context-sensitive is similar, the languages that you get doesn't have the same properties. clear? Clear enough? Okay.
Yeah.
Yeah? No, I don't know how I'm going to get rid of this. Okay, we'll see. So the important things to remember. Here, I just rewrite one term at a time. Okay. Here, I need to decide depending on the context of this term. Here, deterministic L system, it means that I have only one rule for each different symbol. Okay. If I have a rule like A gives B and A gives C, and I need to match this A, I don't know how to decide between these two rules. So this is non-deterministic. I need to give another information to get the decision on which rule I should choose. Clear? Because these are not this is not too difficult, but is that clear? So deterministic, non-deterministic, in a way dual systems, and the contextual L systems. Just to finish, is the fact that you can rewrite more than one symbol, okay, more than one symbol at a time. So if I have a string A, B, C, D, and I can have a rule like BC becomes E. Now, if I want to apply to this rule, I will have this is derived in A, E, C, D. Sorry, A, E, D. Because both symbols were rewritten in an E by this rule. Okay? And due to this, it's a different type of system where you can rewrite more than one symbol at a time. It's much more complex to manipulate.
Because we are far from the notion of growth. It's like reduction.
Yes, it's farther away from the reduction of growth, but it may be the case that sometimes for instance, if two cells are fusing, imagine that this can be the case, you may have this type of thing. Two things becomes one. Okay, so for the notion of growth, it's not directly immediate to think about something. But for instance, in trees, you may have roots or branches that are really fusing with each other. At some point, maybe you need to have this type of operators.
But then we need to consider an order in which to treat the rules, because if there are rules that only concerns B or C, do you first consider those rules, or the rules that considers B and C together?
So, okay. So when we are going to use the L system, normally, if we had a non-deterministic system, like A gives B and A gives C, so this would be non-deterministic, so I cannot decide. But actually, the fact that I write them in the computer in a certain order may provide means to give priority to one of these two rules. So in this case, for instance, I say the first rule is the one with priority, and then when I read this string, I can say if I encounter an A, but since the A gives B is first, I will use this rule first. But in this case, you need to have a mechanism to say that the second rule will be reached, because otherwise, if you apply this, the second rule won't be reached at any point. So it's a bit more complex, but it is a way to get rid of the non-determinism. Okay? Other questions? it's a bit a small passage to the on the theoretical side. We won't stay it too much, but I think if I use this, it's very important to the conceptual understanding of the whole stuff. So this is why I took some moments to be on this.